Welcome to our latest IoT demo. This is a recent project from the partnership between Microsoft and Bentley for Doosan Heavy Industries. And what this application does is it allows engineers at Doosan to monitor and predict the renewable energy output of a wind farm located off the coast of South Korea. So we're going to dive straight into the demo. We start off in the town right next to the wind farm. This was some reality data we added to the project to give the model some context. Towards the left, right off the coast, you can start seeing some 3D models of the wind turbines. Now, there are 10 turbines in this model, and we're going to be able to view the live power produced by each individual turbine. Now, where does this live power come from, the live data? That's a common question, and that's where the Microsoft bit comes in. We have an Azure Digital Twins instance that keeps track of all the sensors connected to each turbine, and we're able to query this data from our iTwin app and present it in a meaningful way. So let's go ahead and see what that will look like. We'll click on this Performance Watchdog tab, and this immediately starts fetching live data from ADT. Right off the bat, you can see the overall power being produced by the wind farm right now. In this case, it's 6,058 kilowatts, and you can see it update as time passes. And then we can zoom into individual turbines to get a more detailed view. So for example, when I select one of the turbines, we can see the power output, and we can see other important values as well, such as the current blade pitch angles, the temperature of the components inside the turbine, and the exact wind conditions experienced by this particular turbine. Over in the power section, you will see that there are 3 power values. There's the observed power, which is the actual power produced, and the 2 other values are based on different prediction models that guess at what the power produced at this time could have been. The physical model uses basic physics and weather, and then there's the data model, which uses machine learning. The big question, though, is how do we make sure that this prediction is working? Anytime the machine learning model fails to accurately track the power produced, we immediately send an alert to the user, which gives them an opportunity to investigate if there are any issues with the algorithm or with the turbine. These alerts are also sent in case there are issues with temperature or just general power production. A second, more detailed investigation can be done when we look into the past. All we have to do is double-click on the power tile, and bam! You can see the historic data for the power produced on this turbine, and you can see the actual observed power alongside the machine learning and physics prediction. For example, in this case, you can see that the machine learning prediction, the power DM, seems to have been quite effective as it's close to the actual power produced. Another important view is this one right here, which shows the power produced by all turbines in the same graph, and this can be used to compare the historic performance of all the turbines against each other. And with that, we are ready to move on to the future. All we have to do is click on this power prediction button, and that kicks off the prediction mode. At this point, what happens is the app fetches weather data from a local weather service and feeds it to the machine learning model to finally obtain the predicted power. And you can see that the clock is flying right now. Why is it in such a rush? That's because we're simulating the next day's power production with the predicted values from the machine learning that we just got. And you can see the play-by-play of the power output of the entire day. And you can see the same data in the chart below. And that sums up all the features of the app. One of the key issues with wind power is that it constantly fluctuates, making it difficult to manage and predict. This app brings together the past, the present, and future data to give a comprehensive perspective of the performance of the wind farm and provide deeper insights into the accuracy of various prediction models. Our hope is to help Doosan optimize the performance of their wind farms and ultimately create a more sustainable future.
Hello everyone, welcome to this webinar. So in this section, we are going to be talking mostly about a single topic and its data. Where is it coming from? Where is it going? What are the different types of data involved in this project and how it all comes together? Now, there are 2 broad categories of data here. The first is the headliner, the IoT data. That includes the data from the sensors, the historic values that we saw, and also the future prediction. That includes the machine learning. And then we overlay all this information on top of our digital twin, which includes the design data for our turbines, for our model, the geographic data, and also the reality data. So let's see where it all comes from. So this diagram broadly shows what all we need to know about the structure of our app. So we have 2 sections here. There is the top section, which is the IoT part, and the bottom section is the digital twin part. Now, in this section, our objective is to get to the iTwin viewer. So the iTwin viewer is the starting point for your application. This is essentially a blank slate. It is a basic application that has a viewport and some basic tools, and you can pull in your iTwin, your digital twin, and start extending it to build your own custom functionality. And in order to get there, we need to first start on all the way in the engineering tools. Now, these are classic engineering development applications for infrastructure such as MicroStation or Revit. In this case, we were given this FBX file. It is a turbine, a wind turbine, and it's just a single mesh. Now you'll see that it's a single element, so we don't have any ways of separating the blades from the turbine. So we couldn't do that spin animation, for example, given its current state. So the first step was port this over to a DGN and break it up into separate elements. That's what we did here. So you can see that now we have a turbine. It's got separate pieces. It's got the nacelle. It has the tower, and then there is the blades. So we split up these elements and group them together to define turbines. We have 10 turbines here, which we have geolocated. So you see these pins right here. These pins detail the location for this turbine, and then the next one. And where do we get these locations from? We actually used Google Earth. So this is the actual wind farm that we are creating a digital twin of. And this is outside, right off the coast of Jeju Island in South Korea. So that's where we got the positions from, and we overlay them on top of our design model. And actually I can turn on the map on this model to see the geolocation. So I'll wait for a sec for that to happen. So right there you can see our turbines, and here is the location on the map. Okay, so this is, as I said, in MicroStation, which is a local application. Our next step is to actually get it on the cloud and create and put it in a cloud-ready format, which is the iTwin. That's the beginning of your digital twin. So let's go ahead and go back to our diagram. We start in the engineering tool, and we're trying to get to the iModel hub. And the step we need to take to get there are these bridges. So what these bridges are, they're called bridges. Now they've been renamed connectors, but essentially these are applications that allow you to push data from a local engineering application all the way into the unifying format of the iModel and the iTwin. So let's go ahead and see what that looks like, the process. So the iTwin Synchronizer is the application you can use to make this happen. There's a project, Wind Farm demo, and the iModel in which we push our files. So turbines.dgn, that's the only file involved in this project. It's the same file that we saw earlier here. So turbines.dgn. We just add this, and all we do is hit this button, synchronize, and it synchronizes all the changes on the application into the iModel hub, is what it's called. And the iModel hub, essentially, it's think of it as almost like GitHub for engineering projects. What it does is keeps track of all the changes that were submitted to get the project to its latest state. So you could have multiple people working on the same project in different workstations, and they could all be doing changes on their local machine, and they can push them in, and we keep a record of all the changes that were pushed in, and then you can verify and see how your combined iTwin looks like. So that's the next step. So let's go ahead and see if once we push our data, let's verify that it actually came out how we expect it to look. So over here, you can see the Connect portal. This is kind of like your outlet for viewing your projects on the iModel hub. So we have the Wind Farm demo project, the same one that we saw. We have our iModel, and you will see the list of changes right here. So these are all the changes that were created to, or changes that led up to the model's current state. And then we can click on this View button to verify if the model came out exactly how we expected. And this pops up in Design Review, this application that's linked to the Connect portal. And this allows you to view your iModel and your iTwin. And over here we can see our 10 turbines, and we can see the reality data. We can also see the geographic data, so we can see our model turned out exactly how we expected. Design Review also has some additional tools, which we're not going to go into. But the key thing you need to note here is that Design Review is an application based on the iTwin platform. And any other application based on the iTwin platform will be able to consume this iTwin data, the digital twin data, and then you can extend it from there. So that is our next step, actually, is to, since we have our data available on the cloud, we can now pull it into the iTwin viewer. As I mentioned, the iTwin viewer is a starting point for any iTwin application. It's a blank slate, just a very basic application that allows you to view your iTwin. So let's switch over to that, and you'll see we were able to load our model, the 10 turbines that are geolocated with the geographic data, into our iTwin. And you can see that it's got very basic tools just for navigation. So this is our starting point for our demo that we saw earlier. The key thing to note here with the iTwin viewer is that it's composed of some services on the back end. So you have the iModel.js backend that provides the infrastructure for hosting your iModel, which is the engineering data, the BIM data in particular, and generates the tiles for it and stores it in Azure Blob Storage, which can be pulled to finally view your graphics and your actual model. Then there's the reality data service for getting your reality data that we saw of the town nearby, and the Bing map for the actual geolocation and the map, the geographic data. Okay, so at this point we have our application in the iTwin viewer, and we are ready to start extending it, and we can add all the functionalities that we saw. The key thing, once you have an iTwin though, is how do you want to actually enhance its value? What other data sources are you going to connect it with, and how are they going to integrate with your iTwin? And that's what we think about when we move on to the next step, is what sort of data are we actually pulling in? And that brings us to our next section. We're going to look at the IoT data, which is what we're integrating into our iTwin. So the question is, where does the sensor data come from? Now the sensor data can come either from actual sensors on field. So we could actually have sensors on the wind turbines, and we connect them to the IoT hub and start pulling data that way. And that's what you would expect in a production application. Or you could use the simulation service, which is a quick and dirty way to get started, which is what we ended up doing in this case, because this is a hackathon, so we just want to get things started as soon as possible. So if you have a simulation service running here, you can see that it's got 10 wind turbines. And the cool thing about the service is you can define your sensors as you want. So we have the wind turbine, and we defined the pitch angles, the wind direction, the wind data that's coming in, the power, the yaw position, and the different temperatures of components within the turbine, the nacelle, converter, and the gearbox. And you can define these to replicate the sensors on field. And you can also define the upper and lower limits of these values, which are then generated within those constraints. And you can see that we have 10 total devices here, and we have 10 messages per second. So each device gets about 1 message per second on average. And when this information is put out, you can listen to it again on the IoT hub, and that's your central point for collecting all your sensor data. So that's what we do in this case. We hook up the simulation service to the IoT hub, and we're able to pull all the simulated data into our central location for managing our sensors. So we can actually view our sensors when we go to the IoT devices blade in our IoT hub instance. And you will be able to see we have 10 different sensors here, and they all have their unique values, unique IDs that we can use to identify them individually. Now, once we have our data in the IoT hub, the next step is to start consuming it within other services. You can do whatever you want at this point with this data. And in our case, what we do is we pull it into this Azure function. Now, this is where a lot of the fun stuff happens. This Azure function is linked up to this machine learning model and the physics model. These models take in that simulated data, and then they can be used to give us the predictive power, both for the ML, the machine learning, and the physics model. And the idea is we use these external APIs. And just a side note, these APIs are provided to us by Doosan, and they are the experts in the industry of renewable energy, so they have their own algorithms that compute this information for us. And just like that, we can have any other algorithm or service to replace and connect it within the Azure function to enhance the value of our Azure Digital Twin. So yes, in this case, we get this machine learning and physics data, and also there's the weather service for our future predictions. And when we are able to pull from this, we can finally start computing our final values that we push into the Azure Digital Twin. Now, what does this Azure function look like? Let's take a quick peek. We're going to go into more detail on the code side in the next section. We're going to go do a code walkthrough and explain the structure of everything. But for now, the only detail I want to point out is that there's this client.update digital twin. Now this function is from the Azure Digital Twins SDK, and the idea is that it can extract all the sensor information, the pitch angles, the wind data, the yaw position, the different types of temperatures that we got from a simulation service, and it can push it into our ADT instance, corresponding ADT instance for those set of sensors, and then it can do the same for our power values. So we have the observer power, and then we have the power coming from the machine learning and the physics model APIs, to get our prediction. And we combine these values and push them into the digital twin for the turbine. Now the question here is, how do we know how this data is structured? What defines this data? How do we define our Azure Digital Twins instance? And that's what we're going to look into next. We go back here. There's this DTDL. The DTDL is the language used for defining different models within ADT. So whatever model you want to start consuming, you can define the structure of it. And the way we define ours is based on our I model or our iTwin. And we can look at, so we have 10 turbines within the iTwin, and they have some custom properties that we need to be, that might lend value into our ADT instance. So we port those properties and different instances of the turbines over into our DTDL, and we use that to generate our ADT instance. So both these models are in sync. The Azure Digital Twins and your iTwin, they correspond to each other, one-to-one. Okay, so this finally gives us the ability to start getting data from the Azure function into our ADT instance. Now, the cool thing is ADT has this thing called the ADT Explorer that allows you to visualize your ADT instance. And we can take a look at that here. So we have the ADT Explorer, and this is our wind farm here. So this is the actual wind farm instance. And we have 10 turbines, and each turbine has individual sensors that give us the relevant information for the blade pitch, for example, the different blades, the temperature values, and all that good stuff. And this view, you can see that there's a bit of overlap here. This is still a work in progress, but if you go to the Cola view, that kind of pops it out and you can navigate better. I personally like to use this view. So here's our wind farm, and then here are the different turbines, and then you can use it to navigate to different sensors that you might want to focus on. Okay, so that prepares our ADT instance. Now we are almost home. The last thing left is the time series insights. Now the issue with ADT, it's great at getting our values, computing all this information, and storing it just like it would be a sensor. So now essentially what happened is that all that external information that we're getting from these APIs are combined with the sensor information and pushed in an organized manner. But the problem is that we only have the latest information. So anytime new data is generated here, it overwrites whatever's written over here in ADT. So we need some way of storing the historic data to get our historic values that we saw, the past view. And that's where time series insight comes in. Time series insights can be hooked up to Azure Digital Twins, and we can start pulling anytime there's a new value pushed into ADT, we can keep a record of it on time series insights, and then we can start generating timelines for historic data. And TSI does have its own portal that you can navigate to start viewing your instance and seeing some of the data. So let's take a look at that. We have the TSI Explorer here. This is our TSI instance. And then we have all the different properties that you would see that you might want to view or visualize the past data for. The key thing to note here is that we're using time series insights generation 2, and this integrates really well with ADT. It's designed with ADT in mind. And what's cool about that is that you can actually map individual properties that we saw from the simulation service and also in ADT to actual nodes within the TSI instance. So for example, this is the power observed by the first turbine. We can view it here. And let's say I want to compare it to the power produced by the third turbine. So we do power observed, third turbine, add that to our list. Expands that, and this is not what I expect. What is going on here? Let's see. What am I missing? Okay, there you go. I just had to reset the timer. So you can see that this is the power observed for the first turbine, and this is the third turbine. And in this way, you can create any combination of properties that you might want to visualize the historic values of. They don't have to be power values. Like you could throw in the opposition in this chart if you wanted, and you could display that combination within the app. So going back to our diagram now, we have all our data sources prepared. We have the time series insights instance for the past. We have the Azure Digital Twins instance for the present, what's going on with the sensor right now. And then we have the Azure function, which allows you to get the power prediction using the weather service for the future. All this data is prepared and it's ready to be pulled into our iTwin viewer. From this point, what we do is we work on this extension, which is a modular way for extending your iTwin viewer and start pulling all this information and creating the custom functionality that we saw in the demo. That summarizes the data flow for the entire project. And next up, I'm going to switch over to Bao, who's going to explain some of the code and do the walkthrough of how we structured everything. So that's it for me. Thank you everyone for tuning in, and I'm going to hand it over to Bao.
Thanks, Roop. Hi everyone, my name is Bao, and my segment will take a deeper dive into the high-level diagram shown earlier by Roop. If you'd like to follow along, our GitHub repository for this hackathon is public and can be found here in our iModel.js meets Azure DT / Wind Farm IoT repository. Just keep in mind that you will not be able to run it locally, since it does require a lot of permissions to resources we can't provide to everyone. So anyway, we're going to be breaking down the application into three main parts: the Azure function, which is the mediator between the IoT hub and the iTwin viewer; the iTwin viewer itself, which serves as the UI visualizer for the wind farm; and the iTwin extension, which adds custom UI components and functionality built specifically for this hackathon. So jumping right into the Azure function, the Azure function has a critical role of serving as a mediator between the Azure IoT hub and the iTwin viewer. It basically aggregates and parses all the data coming from our IoT devices, calculates an expected power output from the physics and machine learning model, and updates our ADT instance with these values. So we'll start with our entry from our IoT hub with the file windfarmiot.cs right here, which is the main entry for our Azure function. So you'll notice at line 47 right here, the function name windfarmiot. This attaches to our IoT event hub connection, this arbitrary name right here, which gets generated on resource creation in Azure. This connection establishes the link to our stream of data from our IoT devices. So once we get into the stream of events, we basically loop through, parse, and process all the data that's coming through. So we get 11 values from each event. The first one being the device ID, which identifies which turbine this data belongs to. And going further down in the process message data, the blade 1, 2, and 3 pitch position angles, the time of the reading, the wind direction and speed, the yaw position of the turbine, and finally the temperatures of the nacelle, gearbox, and generator. So with all the sensor data and the device ID discovered, we do a query to our ADT instance to get the corresponding ID in the Azure Digital Twin. This tells us exactly where to send this update to in ADT. So we generate a patch for all the sensor values and then update the instance right here via update digital twin. So this API is provided to us by the Microsoft AT library. So once that gets patched up, we then call two additional APIs, the machine learning API and the physics model API right here, which are defined in the files mlapi.cs and pmapi.cs files. We won't really take a look at it. These two files just do a fetch to an endpoint provided by Microsoft, and it's essentially a black box which runs Doosan code to generate the expected power output. So after doing so, we generate an additional patch right here for these two values, and again update the values from our expected power. That pretty much sums it up for this function. So in summary, get the event, process the data, and update our ADT instance. The second big function here is the trigger prediction function. So this is where we call the weather forecast API right here. And the endpoint basically gets the predicted wind speed, direction, estimated yaw positions, and blade angles for the following day. This is all the required data to pump into our machine learning and physics model endpoint. We basically deserialize the object, the forecasted data, and then we do some math to interpolate the data. Just because we only get 8 data points, one every 3 hours for the following day. So to smooth out the time series graph, we need to do some interpolation. And once the interpolation is done, we pump all the values, the interpolated values back into the ML and physics model endpoint API. We get the predicted power. And we don't send this up to the ADT instance since this is predictive data. We just send it back as an HTTP response for the iTwin viewer to visualize it. So that pretty much breaks down our Azure function. You can refer to this in the GitHub repository again if you'd like to explore more in detail. So moving on to the iTwin Viewer extension now. Just the iTwin Viewer. This is the UI visualizer for the wind farm, and the iTwin Viewer pretty much comes out of the box from our Add Bentley iTwin Viewer package. We'll briefly take a look at it. The template itself is very configurable, and the only two files we'll actually be touching is the app.tsx file and the ADT datalink.ts file. So the ADT datalink.ts file, the app.tsx file here at the very bottom. These are basically the only lines you'll be touching right here. And this is where we define this viewer component that gets passed in props context ID, the iModel ID, as well as the OIDC client, which defines what our users are able to do with our iModel within this application. Basically, these three props are the only thing you need to pass to the viewer. After that, we have basically a bare bones UI viewport pointing to our iModel. That's it. That's all that's required. So what we did additionally for this hackathon is if we jump into the ADT datalink.ts file right here, this is just a short file that just forwards certain requests to our ADT instance, this URL right here. This is our main connection to ADT. So we need to make requests to this URL for the most up-to-date values. So we need to continuously pull this URL to display within our iTwin viewer, right? So that's what we do here in app.tsx in this function set interval. So every 5 seconds right here, we bind to the event emitter and basically broadcast the data we get from the ADT instance. So at this point, once we get the data, just emit, broadcast, and we can do whatever we want across the application. So one last thing to mention here, this extensions prop right here. So this causes the viewer to attempt to load any extensions found in our build directory once this flag is set to true. So set this to true and you're good to go. Our extension is ready to be loaded. And whenever an extension directory gets put into the build directory of the iTwin viewer, it'll automatically load the extension within our iTwin viewer. So moving on to the extension itself, right here. So this extension is where the bulk of our work is performed. This directory basically defines all the custom components we see in our iTwin viewer that pertains to this hackathon. So you can actually perform all this work within directory iTwin viewer, but extension provides a modular way to carry all the components we built for this hackathon into other iTwin viewers. So in the case a different team would like to use the components, it's very easy to carry UI and functionality over, right? So the extension can be broken down into 4 main parts or components. Just to make things a little easier, the first component being the draggable clock that shows current time and the overall power and a power prediction mode toggle right here. The second component are the decorators and markers we see above the turbines that present the live IoT data. The third component is the historical data we see in the time series insights graph below the viewport. And the last component, our fourth component, the alerts we see when an unexpected power value is calculated and appears to the right of our viewport right here. So going back to the code, we'll jump right into the wind farm extension.tsx file. This is basically our initializer, this wind farm extensions class right here. A big item of interest here is the UI items manager on line 111 right here, which registers 2 widgets we use, the alarms and the time series diagram. So widgets and extensions are basically not part of the viewport. They're on the sides right here. So that's why we only have 2 widgets defined to the right and to the bottom of the viewport. So going further down to this add decorator here. We only call add decorator on the power decorator since the power decorator serves as the anchor for all the other decorators. You'll notice as I scroll, you only have the power decorator here, and on click, it'll show the other 3 decorators. So that's why we only add the power decorator right here. And finally, we go into the render for the clock widget. So this is our initial clock overlay right here. So basically, when the extension initializes, it binds to this entire class and immediately calls on execute, which calls everything within this block and have the extension ready and good to go within the iTwin viewer. So on post build, we just copy the bundle over and have our iTwin viewer automatically load the extension. So where these components are defined is pretty much self-explanatory and follows the directory layout right here. So we'll start with the clock, since this is generally the main entry for users in the application. So in directory clock, we have a clock widget.tsx file. Again, it shows the overall power of the wind farm, the current time, and provides that power prediction mode toggle. So the notable functions here are the add data listener. So this is one of the first consumers of our ADT event emitters, which was initialized in the iTwin viewer. So this aggregates all the power from our emitter, sums it up, and displays it with the update power reading function call right here. If we jump into the update power reading function, variable turbine power, loop through this map, which stores all the 10 wind turbines, sum up the power reading, call set state on the React component, and then display the overall power of the farm. So that's what that function does. And the second main function here is the run power prediction function, which calls the Azure function client right here and makes a request to that trigger prediction endpoint we previously talked about in the Azure function directory. So we load the predicted data and then display the TSI graph here. Once we get the array of predicted values, we basically call a loop every 1 second to animate that moving timeline you see when the power prediction mode is toggled. So if I click the power prediction mode here, you'll see this animating timeline, which is on a loop for every 1 second. So that's how all that works. And I believe the rest of the code is just UI and basic functions to support the React components, so I won't get into detail there. So jumping right into the second component, so going back to components, going into the live IoT decorators that appear above the wind turbines now. So if you're confused about the difference between a decorator and a marker is just a type of decorator that we use to show the data in the 3D space here. It just pinpoints where exactly we need to be showing and what type of, in this case, a div that we will be displaying. So in power decorator.tsx here, we'll go through the power decorator because the decorators for the temperature, the wind, and the blade angles, they all follow the same pattern. So you'll notice this giant query right here. At this point in the code, we actually don't know where the actual wind turbines are yet in the viewport, so we need to make what we call an EC-SQL query to our iModel connection on the iTwin platform. This is just basically a SQLite query. And we ask for the turbine IDs, some associated elements, and an origin. So we use these elements already defined in our iModel to identify the proper turbine to associate our ADT data to, as well as providing the location anchor for our decorators, right? So this is all the information we need from our iModel. At this point, we still have no ADT yet, but this moves on to our next file, the powermarker.tsx. So we need a class to store all the data. So moving on to the powermarker.tsx file right here. So again, given the information from our query that I mentioned before, we can initialize the marker class, which also constructs the associated wind, sensor and temperature decorators that appear up when you click on a single power decorator. So that's where this gets initialized right here. So at this point, we still haven't injected any of our ADT information yet. So what we need to do is configure our ADT event emitter, right? So we need to attach our ADT listener right here. And from here, we can further populate our class with appropriate information, the power DM, the power PM, etc., that will be visualized in the marker. So as we're doing that, you'll note there's one important thing to note here. We do calculate the power error as well here, which is used for our alerts, and dump that into a static variable called the power marker.aggregate error list. This variable is very important and will be used later for our alerts, so I'll go into that later. The rest of the code is just UI work in order to display the markers. The power panel code is just a div, a React component. Let me see if I can write here. So then we just call it in the drawFunc function, which basically is on a loop. So we continuously render that React component for the marker. So that's how the decorators and markers show up right here next to the wind turbines. So now we'll move on to the third component, the alerts. So the alert, which is the right side right here, is basically another React component that uses React hooks. If you recall earlier, we did set a variable called aggregate error list. So we set that as the variable error list within the React component right here. So we use this variable in our use effect. So whenever the React component updates, if you're familiar with React hooks, it basically forces the state to update whenever we receive an event from the ADT emitter. So with that in mind, we go through a bunch of UI logic to bind event listeners to each alert. For example, the on-click for zooms, the toggling of visibility of the decorators, as well as the time series graph. So all of that happens when you click on a single alert, right? So we have the zoom, it shows the corresponding graph, and then it shows the corresponding decorators. So all of that happens within the alert provider. So, right, the rest of the code is just UI work, display markers, etc. So I think that pretty much covers our alerts here. Yep, the remainder of the code is just polish, making the components responsive and looking nice. So the final component is the time series component. That graph you see at the bottom right here. We'll just dive right into the time series.ts file, which is the main function that does the bulk of the work for the data for the nodes. So we have a static function called, load data for nodes right here. And in this function, which is called throughout the application and usually bound to on-click events when we click on like decorators, alerts, or buttons. So this is the main function for our time series. You'll notice at the very top, we also have an environment variable here that points to the TSI endpoint. So we need to make requests to time series insights to provide us the required data to plot the graphs. So asking the endpoint what we need from our TSI graph, we jump into this load data function right here. And this is where we actually get into the finer details of the query for our TSI graph. You might be a little bit confused at this point since we've already made two queries, one to the ADT instance, one to the iModel connection on the iTwin platform, and finally this one to the TSI endpoint. Keep in mind these are all different queries and use different syntax, so don't get too caught up in the queries here. So I'm not going to jump into too much detail here, but you can provide, you can go to the link provided in the comments here to explore more about TSI and its queries. This API is quite new and still in development by Microsoft, so you can go ahead and explore that if you're interested. Anyways, once we pass the query into the URL, we basically jump into the TSI client to get the results. And once we get the results, we call an update TSI graph to actually render this graph you see here at the very bottom. So I believe the rest of the code is just UI work. The TSI, the time series diagram, the TSX file is just a React component, mostly more UI work that binds to the widget. And I think that covers all of our components. And that basically sums up the deep dive segment of this presentation. I know it's a lot of information, but for those interested or may have missed something, I encourage you to take a look at the GitHub repository for more details. The READMEs basically contain everything I've explained so far. So with that, I'll now pass it over to Nathan to go behind the scenes and how we manage to actually get the wind turbine spinning. So that's all for me. Thanks all.
Hello, I'm Nathan Arad, and I'm here to talk to you about the workflow that went into creating the animations that we see on the wind turbines. I'll start off with a quick disclaimer that this workflow was created as an exploratory proof of concept rather than an actually suggested workflow. Please wait to consider adopting this until we have had time to make improvements and optimizations to this workflow. It will save you a lot of headache in the long run. If you have any interest in this, please contact us, and when the time comes, we will be more than happy to work with you on it. Now, as for the workflow itself, it was created using the magic of our render schedule. Our render schedule was originally created for showing a change in the model over time, such as the visibility of certain elements or changing the color of them, or as we are using here, applying a transformation to this time, a transform to a specific element, such as the wind turbine blades. For most render schedules, the workflow moves as create a render schedule and then loop through the timeline. Easy peasy. That would create our animation. But unfortunately, due to the nature of a transform timeline, the backend must be made aware of these changes. Otherwise, you get the issue with this, where the tiles are not updated. You see on the right there, you'll see the original rendering of the element, as well as the updated, transformed rendering of the element, which is not the intended effect we're looking for. So what our animation creation timeline was for this hackathon was create a JSON script, embed that in the timeline in the iModel snapshot, and then re-upload that iModel snapshot to the GitHub or to the iModel hub. And then in the iTwin viewer, we can loop through the timeline and create the animations. So those extra steps are what we're hoping to remove, as well as provide some optimizations to the actual rendering itself. So we can get back down to this just two-step process. Now, as for the code related to this, you can find it all in our GitHub repo under the Wind Farm extension source animation directory. The only file that is actually called at runtime here is the animation timer TS. This is just the logic that is necessary for looping through the timeline and starting and stopping that process. It's not that exciting relative to the actual render schedule. Then the animation UI is just the debug panel I had for visualizing the timeline a bit better. Now, the timeline creator tool is where it gets into a bit more of the meat, creating the render schedule, but it's more of a template rather than the actual script JSON that we can embed into our iModel snapshot. There is also the timeline.json, which is the actual JSON script that we embedded into our iModel snapshot. If you have questions about the specifications of that JSON file, as well as the tool that was used to embed it in there, that tool is in iModel.js, and I go into a bit more detail in a comment in the timeline creator tool. But that's really about as deep as we want to get into it now.